This is fun. I don't usually get to wear one of these cool mics, so this is very special. Thank you all for having me here. This is really fun to be here. This is my 4th time in Ghana, but the last time I was here was 2019, so it's been a while. And I'm here with a few colleagues. We are here for the week to teach oceanography at a summer school that will be held at the University of Ghana. So that's what we're here doing. And I'm the Python person there, so that's why I'm here. So yeah, I'm all about Python, and I'll tell you a little bit about my background here. But this talk today, I'm just going to talk about perspectives on open science, like what open science is, and then I'm particularly interested in the open source software side of open science. So it'll be a very informal talk. I'm just going to talk about some of what I've done, some of my communities that I'm part of, and then I hope we can have a nice discussion afterward. All right. Oh, I should say I do work at NASA, so I'll be talking a bit about what NASA is doing to support open science. But some of my talk does not have to do with NASA either. It's kind of my background as a scientist and other communities I'm in that are not part of NASA. I'm supposed to make that very clear. Okay, so my background is in physical oceanography and climate data science. So physical oceanography means the physics of the ocean. So I used to do research, I don't do as much research anymore in my new job, where I would look at climate model output, and I'd look at ocean data, and I would do analysis on it, and I would use Python to do that. Climate data science I did a postdoc that was called Climate Data Science, and that was really looking at kind of the intersection of the science that we do and the open source tools that we use to do science. So now I'm getting more onto that side, where I'm kind of thinking about what tools can we make available so we can accelerate the science and make science better. So the data that I use in physical oceanography and climate science is very complex. It's like highly dimensional. So we have these multi-dimensional data sets that can be kind of challenging to handle. You don't need to know what this means, but this is one of the many equations in my analysis. This is just pretty complicated, and this is one thing that led me into using open source software. Okay, so I did my PhD with a professor here named Brian Arvik. He started the school that we're all teaching at, and this is Joseph Ansong, and he's now a lecturer at the University of Ghana. So this is how it got connected here. And that was one of the plots that I made in my PhD, where I looked at different energy budgets in an idealized model, and idealized in that square was meant to represent the ocean, but it doesn't look very realistic. You probably didn't know that. So with my postdoc, I got more realistic. I have these nice global maps, and I was also looking at how the ocean and the atmosphere interact. So now I'm at NASA. I'm a program scientist or support scientist, and I work in these teams called Transform to Open Science, which I will refer to as TOPS moving forward, and then the Open Source Science Initiative as well. So, what is open science? Well, this is the definition that the US federal government has adopted as what open science is. There are many definitions, so this is one of them. But I do kind of like this. It's the principle and practice of making research products and processes available to all, while respecting diverse cultures, maintaining security and privacy, and fostering collaborations, reproducibility, and equity. So there's a lot there. But the idea is that open science, we're sharing the science that we do, but we're also making sure that we're not sharing anything that would go against people's privacy. So if you're in climate science, it comes up a little less, but if you're working with health data, you might have people's kind of private health data, you don't want to share that. And there are also all these other cultural concerns. So that's the official definition. But what really is open science? Open science is basically making our data, all the data that we use, openly accessible. It's using open source software, and it's sharing the code that we write. It's sharing all of our results in an open and free way. And then it's the community and collaboration. So this is kind of the process of doing open science, and we kind of share all of these things and make these all openly available. Then we have all these great benefits. So we make our science more accessible and inclusive, so more people can access the science, and more people can be scientists as well, because they have access to the same tools that everyone else does. It will accelerate the discoveries. If we really can collaborate and share everything, we don't need to reinvent things all the time, because we can just start where someone left off and add to it, instead of having to start from level 0. And we also, a big part of open science is making our science more reproducible, which is a big part of the scientific process. When we do science, we want to be able to repeat it and get the same result. And by doing this, we'll make it more transparent, and we'll be able to reproduce things more easily. So ultimately, all of this, hopefully, the theory is, and I believe it, that this will make our science better, and it will increase participation in science and increase the public trust in science. So that's kind of what open science is. These are a few kind of pathways that guided me to open science, and so there are kind of some examples of what I'm talking about. The first one is accessibility to tools, and I don't know if, has anyone here heard of MATLAB? Okay, cool, so you're pretty familiar. So MATLAB is a great tool. I have nothing against it, but you need to pay for licenses, at least we do in the US. And I learned MATLAB when I was in undergrad, and then I took a year and did research in Germany for a year, and that university did not have personal licenses for MATLAB, and so they did have MATLAB, but I had to travel across. I was in Berlin. I had to travel all the way across the city to get to the library so I could use their computers so I could do my homework. And I had been used to having it on my own computer, and I kind of complained and said, wow, that's really annoying. And luckily, some of my German colleagues said, you should learn Python, then you won't need to do that. I said, oh, okay. And that's when I learned Python. So that was kind of my first step into kind of open science, where someone convinced me to learn Python because I lost access to the tool that I was using before. So the other one is scalability. So I mentioned that I'm using really big data sets that are multidimensional. I'm doing a very complex analysis. And the open source tools have been much better at handling that. So I already showed this before. So I'm using these very high resolution global climate models. They're very big. It's a lot of data output. And on some of the analysis that I'm doing, I can't chunk it up. I need a full time series to do like some Fourier analysis and that kind of thing. So it gets very big, and I need to handle big data. They're very complex, multidimensional, and all of these tools were being developed in the open source Python space. And so I found these communities and, oh, this is what I want, this is what I need. So I'll talk a little bit more about that later. The last thing that for me really guided me to open science is the inclusion side. And so this is a story about someone from Nigeria who I met as a participant at our summer school a few years ago, and now he's an instructor. He teaches Python with me. And his name is Mumin Oladipo, and he's really great. If you meet him here, you should say hi. He's not here today. I think he's arriving tomorrow, but he's really great. So he has this great quote that he wrote out. He came to our school in 2018, and he learned about Python. Our school is 1 week, so we're not really teaching, we can't teach much, but what we can teach is, here is what Python is, here's how you can use it, and we'll get it installed on your computer, and then you can go home and really learn it on your own. So he was one of the students that got really excited by Python. He had never heard of it before coming, and he was able to, so he takes data from solar flares, where he puts instrumentation, he collects data. He had made an instrumentation before coming to the school, before learning Python, that used a desktop and used Excel to collect the data, because that's the only tool that he knew about, that he had access to. The problem with that was the desktop consumed too much power, and so it was outside of his research budget. So once he learned Python, he was like, oh, there's something called a Raspberry Pi. I can use a really small computer. I can code that in Python, and I can collect the data, and it takes much less power. It's very small, so you don't have to run a whole desktop to do it. And he was able to set up this instrumentation at his university and a few others. And he's a lecturer there now and is doing really well. So I thought that was a really cool example of different barriers that we're hitting. and how when we're using these flexible open source tools, it gives us more flexibility in what we can do, which is pretty important. It enables new science. Okay, so now I'm going to talk about some open science communities. The first is the shirt that I'm wearing here, Open Source Science, and this is the website. It's opensource.science. It's very convenient. And this is a community that the idea is to bring together scientists who are using software as well as developing the software, be one community, because often we have them kind of siloed into different spaces where science users are trying to use these tools, but they don't maybe have the software background to do it really well, so they're kind of going slowly, and software developers sometimes don't know how to connect to the science community and know how to use their tools to really benefit the community. So this is the goal of open source science, and this is one of the first international kind of events that open source science it was not organized in any way, but we reached out to Manny and others here and said, hey, let's do an event. So they're very excited about this. We have a lot of it is based now on just kind of monthly meetings of these different interest groups. So at the moment we have 3 different science disciplines that meet. And those are kind of our vertical groups, but then we have cross-cutting groups, and those are on the topics of reproducibility and how to map out science, which I think is a really interesting one. Right now, there's not a good map of what tools scientists are using. It's like which Python packages are being used in which types of science. And if we can really help map that out, that would really help both scientists to know what tools they should be using, and also help the software developers to know where their tools are being used and then where they can focus their efforts. So there's a QR code here. I don't know if you do QR codes here. NASA loves them. So there's a QR code there of how to get involved. You can also just go to opensource.science, and there's a link. There's like a little blog post that says how to get involved, and that's where that takes you. So if you want to get involved, they would love it. They love international participation. The other one is Pangeo. This is a community I've been part of for many years, and we call ourselves a community for big data geoscience. We're really trying to, similar to open source science, but specifically in the geo and planet sciences, we're connecting scientists with the software and then also the computing infrastructure that we're using. And I'm going to go into more about that in a moment. This is some of the main software that we use in Pangeo. I don't know if anyone here is familiar with some of these. Jupyter is a big one. They have all sorts of things, Jupyter Notebooks, Jupyter Lab, Jupyter Hub. And Xarray is really great. I'll talk a little bit more about Xarray and Dask. They have really enabled scalable workflows in ocean and climate science, and many other sciences now too. So that's pretty cool. So what is Pangeo? We're a community that's really obsessed with efficient data processing. The people who started it really were just frustrated with the current state of tools, but we could be doing much better. So we have weekly meetings, you have people come in and give talks. So if you have something relevant to the community, we do virtual meetings. You're welcome to join, and you can sign up and we can have you be one of the speakers, which should be really fun. We really like to use interoperable software that all kind of work together. And then we're also looking at the actual infrastructure side. How do we actually do our science? What platforms do we use? So Pangeo Showcase. This is a list of people who presented this year. We actually had someone from Lagos present about data inclusivity. We have a discourse forum that is open that anyone can use. We have discussions there, we post events, things like that. This is the education side of Pangeo, so they are providing tools, which actually is what we are using at the summer school this year to teach Python. This kind of introduction to NumPy, to Matplotlib, to Xarray, some of these tools that are used in our community. There's also a Pangeo Europe group that would be meeting on time in the time zone that would be very similar to here. So maybe that could be this Pangeo Europe in Africa if you want to get involved. And then Pangeo Forge is an interesting thing that grew out of the community that's we're really pushing more toward cloud computing in Pangeo. And Pangeo Forge is basically a way for any user to upload data into the cloud and have it be analysis ready and cloud optimized. Because I don't know if anyone here is using cloud at all, but how we store data on the cloud is very different than how we store it on a regular file system. So, that's in a nutshell what that does. Okay, so I think this is a really interesting concept, and it's like the main concept kind of behind the Pangeo community, and it's how a lot of us in specifically the climate space, but other sciences are shifting toward. So this is the traditional download model. So here we have step one, we download some files. We have it then on our local disk, and then I analyze it on my personal computer. This system works fine. If you're using megabytes, of course it depends on your internet access, but if you're doing megabytes of data, this is fine. This works well. You can download data really fast. You can analyze it really fast. If you have gigabytes, it gets a little slow. It's not great, but you can often do it. If you have terabytes of data, it gets pretty rough. And if you have petabytes, which some of our climate data is, exactly, yikes. It does not work at all. We cannot download that. So this is a Pangeo community of like, we need something else. This just doesn't work. So what we've gone for is this cloud computing. So here we are, if we're scientists here using our laptop, we can go into our browser and we can connect to the cloud through something called Jupyter Hub. And that gives us an interface to the cloud. And Jupyter Hubs can be set up to do lots of things. You can run things that are not Jupyter related. If you're used like Jupyter notebooks, which I am, you can run that. But you can also run RStudio. You can actually run MATLAB through Jupyter Hub in the cloud. So it's basically just, it uses your browser, and then you can interface the cloud using Jupyter Hub. So as a user, I would click a button, I'd open up my Jupyter Hub, and then I'd have access to my cloud computing cluster, where I'm using my tools like Xarray, that's the main package that I use. And then what is really great here, we have something called Dask, which is for parallel computing. You can use Dask on your local computer, on any server. You can also use it in the cloud. And Dask is for parallel computing. And so that's where this comes in. So I can connect, I'm on the cloud, I can do something, and I can say, okay, run this in a parallel way. I don't have to know how to do parallel computing, and it will all theoretically work. It doesn't always work, but it works most of the time. And then what that will do is it accesses data that's in a cloud object store. So I'm probably getting a little bit in the weeds here, but happy to talk about this more. So we don't, in the cloud, we don't store things in files, we store them as objects, which is a little different, although it doesn't, as a user, it often doesn't really matter. We store our files as ZAR, which is a cloud-optimized version of NetCDF, which is, I don't know if you're familiar with that, but that's basically the preferred way to store multidimensional data sets in the sciences. So ZAR is kind of the cloud version of that. And what it does is it stores your data in little chunks, and then it can access them really quickly. So anyway, that's kind of that in a nutshell. I'm happy to discuss that later or during lunch or anything like that. So here is an image of what the Jupyter Hub looks like. I mean, it just looks like Jupyter Lab, if that's something anyone's familiar with. You have files here. So this here is actually our hub that I set up through a company in the US that does this for educational purposes, and this is the one for our school. So this is the intermediate NumPy tutorial I can go through. But yeah, this is what it looks like. And so it's just the browser on my computer, but I'm running it on the cloud. It's cool. And this is what it would look like when you're logging in. You just click login, and once you have to have access to be able to log in, but it makes it really, really easy. I already talked about Pangeo4, so I think I will skip that. So one thing that I think is really interesting and an important way that we've changed how we're doing our scientific computing is by using Xarray and Dask, and there are other tools. These are the tools that work best for the data that I use, the multidimensional data. So Xarray, it's an n-dimensional labeled arrays in Python. It makes it really easy to work with scientific data or really any data because it takes in the metadata and you can say, I'd like to average over time. and I don't need to know which axis on the data is time. Like previously, we would have to say average over axis 2, or axis 0, or whatever one, but we'd have to know which one is time. So this makes it much easier. I can just say like dataset.mean time, and it will do it. X-ray and DAS working together, we can do something that's called lazy computation, where we're not loading in the data, because as I said, we have really big data sets, but we just load in the metadata. And so the metadata tells us like what variables we have and how big they are, all of the actual information that me as a user really needs to interact with the data. And then it doesn't actually do any computation on the actual values of the data until I tell it to. So I read in the data, I can have all this lines of code. I can say I want to add 2, I want to average, I want to do this and that. And then at the end, I can say there are a few commands that will actually trigger the computation. And so that would be something like, I'm going to do something and then I'll .compute. That would then trigger a computation to run all the steps that I just wrote. Similarly, if I say .plot and kind of create a figure, it'll actually execute the computation. And this is really powerful because it means that I don't have to actually load in the data to read what I need. I can wait until the end, and then these tools only access the specific data that I need, and then DAS parallelizes it. And so often what I do is if I'm on my, well, I guess I usually do this on the cloud. You can do it on like a high performance computing system as well. I have my kind of cloud instance. It doesn't have a whole lot of memory, so I don't need to load all of it into memory. I'm going through, I say .plot, and it triggers a computation, and sometimes it needs to pull in a lot of data, and then I'm maybe averaging over a bunch of dimensions, so I'm kind of squashing the data, so my output will be very small. But DAS works on kind of an external cluster, so I can just call it, and then it will run it in the cloud elsewhere. So I don't have to have any of that memory in my own instance. It goes off into the cloud, it does a computation, and then it comes back and gives me the result. So anyway, I hope that's interesting. I find this very interesting. Okay, now I'm going to go to part of the talk of like what I'm doing at NASA, in case that's interesting. I'm going to kind of go through this quickly, but happy to talk more. So we call at NASA, we have open source science and open science. They're based, I don't know what the difference is. I use them interchangeably, but anyway, just so you know. So basically, we're talking about open science at NASA. So we have some, nice big pictures. NASA's looking ahead at really big challenges, and we really think that we need to be working together more. So we need more we science rather than me science. And we think that the best way to do that is by sharing all of our science, all of our data, all of our results, aka open science. So we want more people to be able to participate in science. We want more eyes and more brains to be thinking about the science that we're doing so that we can make sure we're asking the right questions and getting the best results. So here are a couple examples of open science. This one is open data. I really like this one because I really like birds. So this is a data set with some radar data. It's really old. It goes back many decades. And it used to be stored on physical tape because that's how we had to do it many decades ago. We didn't have the cloud or big servers to store our data in. More recently, that data was put onto the cloud, so it was made much more easily accessible. You didn't have to have physical access to the data. And that radar data was mostly used for weather. So we often do radar so we can see storms coming through, so kind of for meteorological research and analysis and prediction. Once they put it on the cloud, there was a group of scientists that said, oh look, we can actually use this data to see bird behavior. This very specific bird, the purple martin, does these big roosting events at certain times of year where they have hundreds of thousands of birds all together. And so there are enough of them that they actually reflect the radar. You can see them in the data. And so this research team was like, we can use this data to look at birds. So it was a great example of making our data open means that people are using our data in different ways that you may not even think about. Another example is, this is the James Webb Space Telescope, which you might have heard about. It's been sending back some pretty amazing images in the last year or so. So they did an early release of the data. NASA announced this ahead of time. there's this group of hundreds of scientists that said, let's all really work together and see what we can get out of this first new data that we're getting. Really, really amazing data. And so they said, great, we hope to get maybe 5 or 6 papers out of this. This will be really great. They ended up getting more than 40 because they worked so well together. And one of them, we always like to say, was looking at carbon dioxide on an exoplanet. It was the first time that they actually saw a signature of carbon dioxide on an exoplanet. And we need carbon dioxide to have life. So this is the catchy tagline is, first step toward finding life on another planet. We have not found life on another planet, but maybe we will. You never know. In the team that I'm in, we're looking at a bunch of different aspects of open science. And we are a government agency. So a lot of it is looking at the policy side. So we're kind of saying, like NASA's always had openly available data, but now we're really getting into the details of what does that mean? How can we make that data really readily available? And there are policies now that are saying, here's how to make your data available, and you have to follow these if you want to get funded by NASA. We're looking at incentives, so that can be in the form of financial incentives, providing funding. It could also be in terms of career incentives, making sure that it can take time to add metadata and share your data in a publicly available way, that is taken as a positive thing when you're applying for jobs, that people look for that kind of thing. And then we're looking at the actual physical infrastructure, the computing services, and then the community side is where the TOPS, Transform to Open Science, comes into play. So TOPS is really looking at the adoption of open science, and I mentioned this, oops, I didn't update that QR code. Well, don't go there. But we're doing a bunch of different ways to kind of engage the community. And this is an interesting one where we are at NASA, which is a US government agency, so we're going to prioritize NASA-funded scientists. But the goal of TOPS is actually to be a kind of global community. So we've connected with a lot of other players in various countries around the world. So you're welcome to join any of these. So we have like community forum every month on various topics, monthly newsletter, all of those things. So if you're interested in this, you can definitely join. We're starting a curriculum for open science that will be probably released early next year, and it's free for anyone. It'll be a MOOC, so a massive open online course, so anyone can take it on these kind of topics. And if you want information about that, you can scan this or go to this website. And then once you finish that, you'll get a little badge at the end that says, you've completed this NASA Open Science course. So that'll be fun. And I mentioned this is very US centered, but the White House announced that this year, 2023, is a year of open science, which is very exciting. A bunch of 15 of the US federal agencies have signed on. And I mention this, I know it's very US centered, but I mention it because there is a lot of momentum right now around open science. And so Python, open source software, other aspects of open science are getting much more kind of into the public space in the US at least. And so I think we're going to be seeing in the next few years a lot more action around this, hopefully some funding and all of that. So that's why I just wanted to mention that, just so you all know what's going on in the US, that open science is being really pushed into the major leagues. Okay, and I like to end with some really great NASA photos because I work at NASA, that's like the best part. So yeah, some inspiring quotes like, keep building code, you guys are awesome. Thanks for all the contributions, and I will end there. Thank you.